This entire unit is about solutions, so things dissolved usually in water, not always in water, but almost always. And those are always called solutions. So solutions, definition-wise, would be a homogeneous, remember homogeneous mixture from the beginning of the semester means you can't like see the different parts of a solute, that's whatever the minor part is, or usually the thing you're dissolving, in a solvent, the thing that's the major part, again, usually water that we're dissolving in. A solution doesn't actually have to be liquid. There's other types of solutions. It's really just something dissolved in something else. Okay. Again, though, homogeneous mixture, so you're not gonna be able to see the different parts. So an example would be 6 molar hydrochloric acid, which is something that we have in the stock room and we use all the time, right? If that's the case, we know molarity is moles per liter. So that means I have 6 moles of hydrochloric acid, the solute, in every liter of water or solvent. Okay, so solute and solvent are two terms you're going to have to be able to identify the difference between, and I'm going to use a lot. So when things dissolve, so we're going to get a little bit into the solution process and what it looks like when you dissolve something, specifically on the particle level. So okay, so this is just a short little video of what it actually looks like on a particulate level when you put sodium chloride or salt in water. We've kind of talked about this process before.
When an ionic substance, such as sodium chloride, is placed in water, water molecules interact with the ions on the surface.
Now, I'm going to pause it there for a sec, because one thing I want you to notice, again, things we've talked about before, is that the red part of the water molecules, or the oxygen part, which is a little bit negative, is attracting to the positive ion, or the sodium ion, and pulling it away from the crystal lattice. And then if you look at the negative part, the white parts, or the hydrogens, which are a little bit positive, are going to attract the negative chloride ions and pull those apart.
If the salt is soluble, the attractive interactions with water molecules overcome the ionic attractions within the lattice. The solvated ions move off the surface and become separated in solution. Notice that water molecules cluster about the anions with the hydrogens directed toward the negatively charged ion. On the other hand, water molecules interact with the positively charged cations through the lone pairs of electrons on the oxygens.
Okay, so turn that on. Okay, so that was really like the ion dipole force, or when things are dissolving. So we're going to talk about the energy associated with that, or the enthalpy of solution or dissolution. There's really 3 processes going on if we break it down. So there's attractions being formed and attractions being broken. And whenever you break something, it's endothermic, and whenever you make something, it's exothermic. So the energies of those, when we put them together, are going to determine if something gets hotter or colder when it dissolves. So you might have noticed a good example is like a hot pack. Once you break it and those things dissolve, it actually releases heat, or a cold pack, the opposite. And it has to do with the energy of those attractions in the thing dissolving in the water. So there's really 3 forces at play that we have to take into account. That there are solute attractions. So the attractions in the thing you're dissolving. So if we're talking about sodium chloride, it's the attractions between the Na pluses and the Cl minuses, right? That in this case is an ionic bond. Okay, those things are attracted to each other. There's also solute-solvent attractions. So when the Na pluses and Cl minuses attract to the water molecules, that's that like ion dipole force, or water and the ions attracting. And there's also solvent-solvent attractions. So the water molecules attracting to each other, those hydrogen bonding forces. Okay, so all of those forces are things that we have to take into account. So the factors that affect the energy associated with, we call it dissolution or dissolving. Some are endothermic and some are exothermic, like I mentioned. The lattice energy of the ionic compound is going to be an endothermic process, because we have to break this Na plus Cl minus bond. We have to actually pull those apart, and it requires energy to break a bond. Okay, so that part is endothermic. Whereas those ion dipole forces between the water and ions, those are new attractions being made. Those are going to be exothermic. So again, whichever one of those like wins out is going to determine if it heats up or if it cools down. Okay, so lattice energy, I'm just going to talk about that for a sec, because that was in one of our other units. If it's got stronger attraction, so +2 -2 versus +1 -1, it's going to have a stronger lattice energy, but it's also going to have a stronger ion dipole force because of those attractions. So the ion dipole force is the intermolecular force between the water and the ions, as we've said. And then you might have heard this term hydration energy before, or if you read in the text, it talks about hydration energy, and that's the energy of the interactions between the waters and the ions. So it's the energy associated with the ion dipole force. These two kind of like go together. So it's talking about the attractions between like the negative Cl minus, oh, this is Kf. So this would be F minus attracting to those partially positive H pluses, or the K plus attracting to the partially negative oxygens. Okay, so that is the energy associated with that is the hydration energy, and the intermolecular force that we're talking about is the ion dipole force. Okay. So again, talking about that energy, there's three steps, or there's three attractions that we have to account for in the dissolution that I like this picture because this is our solute, okay, the red thing. This is our solvent, the blue thing, and then we're going to put the red thing in the blue thing and it's going to be dissolved. Okay, so these things attract each other. The red things have their own attractions. The blue things have their own attractions. And then when you put them in there, they have attractions as well. So those are the three pieces of dissolving something. So dissolution again means dissolving. So in order to dissolve something, what we have to do is we have to break up the solute attraction. So we have to like break up the red attractions. We also have to break up some of the blue attractions. And then when we put them together, they make new attractions. So remember, breaking things is endothermic. Those two things require energy. And making things is exothermic. It releases energy. So of those three steps, you can think of them for dissolving something. Two are endothermic and one is exothermic. Again, that balance, how big endothermic or exothermic they are, how much energy is going to determine overall if it's endothermic or exothermic. So I mentioned a hot pack earlier. If it's a hot pack, that means it's going to be exothermic overall. So that must mean that this step 3, the only exothermic one, releases more energy than was required to break up these solutions. Okay, so step 3 would release more energy than 1 and 2 require. So again, whichever one wins out. So I like this picture here because remember, those first 2 steps are endothermic and the last step is exothermic. So first, like separating the solute particles, so breaking them apart, not necessarily breaking bonds, but spreading them apart, like intermolecular forces most likely, but it could be bonds as well. And then also separating the solvent particles is the second step. Both of those require energy, and then you put them together, they make new attractions, and it's exothermic. And then say if these two added up are bigger than this one, then our net difference is positive. So that would be an endothermic process overall. If this one was bigger, then this would be larger, and then that would be a net negative delta H or enthalpy overall. So it's really based on those 3 things going on. Now I am going to just very briefly mention things that are insoluble, right? Remember, we had our solubility chart, and some things are soluble in water and some things are not soluble in water for those ionic compounds. What makes them soluble or not has to really do with their lattice energy. Things that have really strong lattice energies, water's not going to be able to pull those apart, and those are the things that are going to be insoluble. So a lot of the times it has to do with the charges, right? +1, -1. This one is always soluble, but PBS is not soluble, mainly because it has a +2, -2 attraction there. So that's kind of what makes things soluble or not soluble, and it really has to do with the fact that like separating those solute particles requires so much energy that it's just not going to happen.